Good afternoon, everyone. I'm Gwen Nero. I lead corporate relations and innovation at Scripps Oceanography, and I'm standing in for the chair for the Scripps Technical Forum this afternoon, Douglas Alden, who's out in the field today. I want to thank Doug as well as my colleague Vanessa Scott for their contributions in bringing in our guest speakers for the Scripps Technical Forum. Today we have a presentation by YSI, but first some technical items for our webinar. Please keep yourself on mute unless you've got a question to bring up. You're welcome to chime in with questions or comments during the presentation, either by unmuting yourself. You're also welcome to use you'll see both the Q&A and the chat feature. I'll be providing that technical assistance during the meeting. If you have any issues hearing or seeing anything, please also feel free to use the chat feature there, and my colleague Drew or I will lend assistance. Today's presentation will be recorded, and you can find it after today on the YouTube channel for the Scripps Technical Forum, which you'll find on the STF website, which is sdf.ucsd.edu. And I'll point you to that information at the end of the talk today too. So with that, I will stop sharing my screen and I will briefly introduce our speakers. Today we have a presentation by YSI titled Beyond Sondes, Using Autonomous Vehicles to Survey and Study Harmful Algal Blooms or HABs and Chemical Waste. And they'll be presenting two unique case studies. Our speakers are Tom Goucher, Product Manager, Adam Willingham, Sales Representative, and Dr. Stephanie Smith, Product Segment Manager, all with the Integrated Systems and Services team for YSI. Dr. Smith will be sharing with you more about today's agenda, as well as the brief bios for our speakers. So with that, I will hand it to her. Thank you.
Thank you very much, Gwen. I trust everyone can see the slide on my screen, right?
Looks good.
Very, very good. Moving forward then, of course, the agenda is I am going to introduce you to the team that's presenting to you today. And we're pretty excited to talk to you about two case studies that we have just done in very recent months. So this is actually very fresh information. We're excited to make you folks some of the first people we're sharing it with, because we'll really appreciate your feedback. And of course, we'll welcome questions at the end. But as we're changing speakers and, if you have questions, we're happy to keep it pretty informal and keep things very interesting for the audience. So feel free to interrupt us, Gwen, if you see something that you think would be interesting to address when we're on those changes in between speakers. So I am your host today, basically. We really appreciate the invitation from Scripps. It's a real honor to talk to such an esteemed group and present some of the work we're trying to do, and of course our technologies. I've been developing technologies for over 20 years. My core expertise is in microbiology and harmful algal blooms, having gotten my bachelor's and master's in Missouri before going on to Ohio State for my PhD. I've done a lot of work in sensor development, including some of the sensors you're going to see today. I'm joined by my colleague, Adam Willingham, who has over 20 years of experience in the field. He has a bachelor's from California State in Fullerton, and he's done a lot of work. He has a lot of field experience, well aligned with some of the experience of the folks at Scripps, in fact. And he's done a lot of installations and a lot of projects in ocean and coastal environments. We are joined by Tom Goucher, who's worked for YSI for almost 20 years now. He is really, he's an electrical engineer by training, but really really an expert in systems design and putting together these very complex systems. He's done a lot at YSI, and presently he's what's called a product manager, helping us get the right products into the market, but really doing that by listening to customers and scientists about what they need products to do. So I'm going to go ahead and hand it over to Tom, who's going to tell you about our first project.
Thank you very much, Stephanie. I appreciate it. And thank you to everybody for attending today. It's great to meet you all and talk to you all. So Stephanie, if you go to the next slide for me, please. So the application I'm going to talk to you about today is a place called Brayton Point. Brayton Point is in Mount Hope Bay, which is on the southwestern coast of Massachusetts. It sits directly across from the city of Fall River and its 90,000 inhabitants. Stephanie, next slide. So the history of Brayton Point is that it was formerly the home to the largest coal-fired power plant in New England. And it ran there for years. And in 2017, the plant was decommissioned and it sat dormant for 2 years. And then in 2019, it was demolished. And then since then, the port has been used, as it's a deep water port, has been used for scrap metal operations. Next slide, please. So in early May, mid-May, I was made aware of an incident that happened at the port. One of the large ships that comes in to load and offload scrap metal had a fuel leak, and it leaked into the bay. Initially, containment booms were put out to control the leak, but later on they were removed and they allowed the fuel to dissipate into the bay. And they actually used a small vessel, a small boat, to drive around through the spill to actually dissipate that spill. And you can see that in some of the pictures here. So next slide, please. So we actually have an office here in Fall River. That's where I'm situated. And in late May, on the 28th, we mobilized to go out and survey the bay to see what we could find. So we utilized YSI's rQPOD system, and it was equipped with an XO2S sonde and a handheld XO device with GPS. And we utilized the following sensors. So we had a conductivity temperature sensor on there, a total algae sensor, PE, so chlorophyll and phycocyanin. We also had an fDOM sensor, and that's probably one of the most important sensors we wanted to get into the field. fDOM is field dissolved organic matter. And we also brought a pH ORP sensor. So the question was, what can we see, and can the fDOM sensor see the fuel, the oil spill? Next slide, please. So before we go any further, I wanted to just briefly tell you what the rQPOD is. What did we bring into the field? So the rQPOD, it's a remote surface vehicle. There is an option for autonomy, but realistically, it is the things you see in the top right. So it's the power motor controller system and the 2 thrusters, along with that remote control. That is the rQPOD. It's designed to go on to any floating platform of reasonable size, and we offer platforms for it, torrent boards, as we call them. Basically, they look like boogie boards, or the size of a boogie board. And we offer modular different payloads for them. So there's the ability to put in many different sensors, from water quality to current profilers to side scan systems, and then we have many different GPS options. And based off the design, it's basically they're universal mounts, so customers can take these systems and swap out sensors pretty rapidly. So one system, one payload, or one torrent board can outfit many different sensors. And there's some examples of some of the sensors at the bottom. We have the Sondes M9. The thing laying on the rocks is a side scan sonar. We have the Sondes RS5, and then we have all the different EXO sensors. So next slide, please. So what was the system that we brought into the field? So this is a little deeper look at it. So like I said, we had the EXO handheld, and you can see that in the top right picture. That's it right there. And it was connected to an XO2S sonde, the one I mentioned earlier. And we set that up so the handheld was logging all of the data. And the handheld has a built-in GPS sensors so that we can GPS correlate all of the data. We set the handheld to sample at 1 hertz, which is the fastest it can sample. And then we also set the filtering that's in the sonde on the data collected to rapid mode, which is basically 1 hertz as well. So we wanted to get as much data as fast as we could to get a spatial representation of the bay. Like I said, we had the XO2S with the sensors I mentioned earlier, and we utilized an option for the rQPOD called the XO whale. The whale is basically a flow cell that mounts onto the board, and the sonde is mounted into that. The top right picture, you can see the top of the sonde with the penetration through the board, and then the bottom picture on the bottom left is the bottom of the whale. That's the bottom of the flow cell. It's a little hard to see, but water will flow through the front of that, and it goes across the face of the sensors, and then it exits out the back. So, next slide, please. So the area we first surveyed was the bay. And when we surveyed this, due to the size of the bay, we ran the rQPOD in autonomous mode. So that's how we get those nice straight lines and even spacing. The spacing was set to, I believe, about 25 meters, which for what we were trying to do was the resolution was sufficient enough. If we were doing something like a side scan sonar or a bathymetric survey, we might have done tighter lines like 10 meters. But for what we were doing, the 25-meter resolution was perfect. Next slide. And then after we completed the bay, we did a small estuary, which was it's in the northeastern part of the bay. As the area was very small, we didn't use autonomous mode. We ran the boat in remote control. And we tried to be as thorough as possible to get into the estuary and drive through it. But you can see it's relatively small. And there definitely is a difference in the lines. You can see the difference in the lines. These red lines are actually where the boat drove it, where it was driven. So you can see they're not as clean as when it's in autonomous mode, but it's still good and it still works perfectly fine. The data comes out amazing. So next slide, please. So this is some of the data that we collected, just 3 of the parameters that we collected in the bay. Now data, when you're running any one of our systems, data can be viewed either in real time, depending on the software and the system you're using, or via a direct download. So after you run your survey, you can pull the vehicle in, connect to it, and download data. We did a mixture of both. So next slide, please. So having the system collect data in real time, it gives you the benefit to be able to see what's going on in real time so that you can identify areas of interest, hotspots maybe, and then you can retask the vehicle to go and look at that in more detail. So it affords you the ability to see what's going on instantly and then make instant decisions. And then obviously you can look at areas of concern in more detail and get much more resolution on that data set. Next slide. So this is the total picture of the data that we collected that day. You can see that there's the bay data that we collected, and then there's the estuary. And what we used is a Xylem brand software. It's called HYPACK. And we actually use that for mission planning, but also for data collection and real-time data analysis. But we were able to take those 2 separate data sets and then stitch them together into one complete look at the data. So it's a pretty powerful tool for looking at data and also planning missions and running missions. So now I'm going to turn it back over to Dr. Smith, who's going to look at the data that we actually collected and kind of give you an interpretation of what was going on and what you can read from it. So thank you very much.
Thanks, Tom. One of the reasons we were so interested to show you guys these data is particularly because of the fDOM data, and that's what I'm going to focus on. Normally, you would probably hear me talking to you a lot more about the algae data, but we'll have some good algae data to show you yet. So why fDOM? Some of you may already know that most carbon on the planet is stored as a huge reservoir of dissolved organic carbon, or DOC, in the ocean. And the majority of this is recalcitrant DOC that's been stored for eons, right? So you know, that's where most of the carbon on the planet is stored, is in this DOC. There is an ongoing delivery of carbon, though, into coastal waters from rivers. That's a major source of carbon flux. And that includes what we call fDOM, or colored dissolved organic matter. There is a fraction of fDOM that is also fluorescent. That is what we call fDOM, is fluorescent dissolved organic matter. So an interesting thing is, depending on the environment you're in, 20 to 70% of dissolved organic carbon actually could be fDOM. And so this raises the question, in certain environments, can you use fDOM as a surrogate measurement for dissolved organic carbon, for which we have very limited ability to do sensing in real time? So we actually did do something very similar to this when the fDOM sensor on the EXO platform was new. Eric Smith and a team in South Carolina, in Georgetown, South Carolina, did a study to determine that the fDOM sensor could be used as a surrogate for for DOC in coastal environments. An interesting thing they figured out was you did need to do corrections in their study for turbidity and temperature. Now, if you're not familiar with fluorescence, one of the things you have to be very aware of is that fluorescence is inversely proportional to temperature. And we don't automatically correct for that in the sensor, because you wouldn't know precisely what that relationship is in any given environment. So what Dr. Smith's team did, the other Dr. Smith's team did, was determine what correction factors for temperature would work in their environment. Likewise, turbidity can be an interfering factor when you're using the fDOM sensor. And that's because turbidity, of course, can include light. It can include light coming out of the sensor. It can include light going into the sensor. So they figured out how to do those corrections so that they could get very reliable measurements of fDOM that would be representative of dissolved organic carbon. And this is an example of some of the data they collected. In this case, what they are reporting as DOC is actually being measured in real time with the fDOM sensor. So this is the corrected fDOM measurement. And you can see that sometimes when you get changes in salinity, a lot of those are associated with freshwater influxes into this estuary. And a lot of times those are where you see those spikes in dissolved organic carbon. So this paper is online if you want to learn more about that. In our study, one of the things I wanted to make you aware of is that the fDOM sensor is one of many types of technologies that can measure fluorescence on what's called the EAM spectrum. So that is the excitation and emission spectrum. Fluorescence, of course, includes an excitation wavelength. In the case of the EXO sensor, the excitation wavelength is at 365 nanometers, but the emission wavelength is at 480 nanometers. So what this basic EAM spectrum is showing you is that these different peaks, and I would strongly recommend looking at this paper, these different peaks represent different types of matter that fluoresces on the EAM spectrum. So peaks A and C, for example, represent terrestrial sources of human and fulvic acids. Peak C typically is what contains the highly colored humics. A has the deeper UV absorbing humics. But this box is the peak that usually the fDOM sensor is most closely associated with. Now, we knew also, though, that crude oils also fluoresce in about the same range. And so this was the basis for our hypothesis that if you're in an environment where you don't have a lot of other dissolved organic matter, the fDOM sensor could probably be a pretty good surrogate measurement for crude oil. And it certainly appears that's the case when you look at this example that Tom just showed you. There's definitely, and the units here, by the way, for fDOM are relative fluorescence units. Some of you may be familiar with quinine sulfate units that are also part of the fDOM output, but you can definitely see that there is heightened fDOM in the region near the leak on that tanker. But it's really important to point out that, wow, you see a lot of fDOM over here in that estuary, as you might expect. And I point this out because it means that if you're in an environment that already has a lot of fDOM, this approach might not work for you. But if you're in a coastal environment or an ocean environment where you might not expect to see a lot of fDOM, this could be a really useful tool for looking for oil leaks, actually. But even outside of that application, the fDOM sensor is a really excellent tool for looking at dissolved organic carbon overall, we believe. So what we learned is that the fDOM sensor definitely could detect crude oil in this application, but it couldn't tell, it's not going to be able to tell the difference between crude oil and true fDOM material that is in your water. So it's an effective broad scale surveying tool, particularly when you couple it with one of these vehicles. But we would probably advise that you also maybe ground truth it with a grab sample or another sensor. So that is one of the case studies we wanted to tell you about today using one of our vehicles, the rQPOD. So next, I'm going to hand it over to Adam Willingham, who's going to tell you about another vehicle application where we're looking at harmful algal blooms.
All right, thanks all. I have to forgive me. My neighbors just got 2 puppies, so I do not run a kennel, but they are active right now. So if you hear barking, it's just my new neighbor's new dogs. Really quick, just a little background. Tom and Stephanie approached me a little while ago to see if I knew anyone that would be interested in using one of our vehicles as a service. Stephanie will talk about a little bit about the vehicles that we have. And she mentioned they have a higher price point, but this way, you know, can we collect the data for it? So I definitely had something in mind. Through my experiences in Southern California, have a couple connections, so I knew who to talk to. So I actually got a hold of Dr. Karen at USC, who I know as a harmful algal bloom marine scientist, but I didn't know that he was in the realm of freshwater. So he's doing a project, and we actually were lucky enough to team up with him. And the project, thanks Stephanie, the project includes Southern California Water Research Project, also called SQUIRP, USC, Xylem, and also we're sponsored by the band of Pomo Indians up there in Clear Lake. So a little background on Dave Karen. Like I said, I've known Dave luckily for about 20 years. So when the question came up, you know, do you know someone that could benefit in it using this product or this vehicle, definitely brought Dave into it right away. As you can see, he's got a varied background. And most of his work that I know him from is working with Pseudonychia off the Southern California coast. But he's actually opened his own kind of remote lab and set up areas in Clear Lake. Next slide, Stephanie. Now the project goals for Clear Lake were 5 steps basically. Overall goal was to conduct field survey to document and characterize the physical and chemical drivers of cyanobacteria. Establish the dominant taxa in the area. As you're going through the lake, you can seriously see different shades of green, purples, just on the surface alone. So it's very diverse in the area. Identify factors stimulating the cyanobacterial blooms and cyanotoxin productivity. Yeah, there's just a lot of activity on the lake. Conduct molecular investigation of microbial communities. He, like I said, he has these set to go in his little cabins up there, Airbnbs, and they set up an entire lab for these projects. Then guide approaches to manage and mitigate harmful algal blooms in Clear Lake. I'll kind of explain a little bit about Clear Lake in a second. The mission we're going to talk about today, or a couple of missions, are to support the project for Dave Karen. This started in, I'll go next one. This started in spring of 2020. We're supposed to start in spring of 2020, but had to be reduced to a single month in August due to the COVID outbreak and the pandemic, where basically he was going to go monthly for 6 months and he had to squeeze it all into August. So when you look at Clear Lake, the picture here, it's broken into basically 3 arms of the missions that we did, plus Konocti Bay. The 3 arms include Upper Arm, Oaks Arm, Lower Arm, and then D would be Konocti Bay. Just a little background on Clear Lake. Just in this project alone, I learned myself that the age of the lake is 2.5 million years old, which makes it the oldest lake in North America. What's also crazy, doing these studies about toxins, it's also known as the bass capital of the West, where it has some of the largest bass fishing competitions in the Western United States. Even though California Environmental Health and Hazard Assessment has issued safety warnings for any fish caught on the lake due to elevated mercury levels. And we all know that eutrophication, climate change, and other global factors can drive HAB events. But when you look at a single lake system like Clear Lake, how well do we understand the micro-environmental impacts? Why, for instance, might there be different species dominating, section B versus section C? If C and D are in the same organisms, why might they producing toxins in some areas they don't? How should this drive decisions for monitoring, managing during blooms? Next slide, please. And I'm not going to pretend I know how to pronounce most of these. But these are the players they're seeing in the area, the cyanobacteria. Just from being on the lake with the team, though, I mean, it's like you can go just a couple meters and you'll have surface aggregates of either species, all species mixed together. It's a crazy hodgepodge of trying to get the big picture. Next slide. And like I was talking about that hodgepodge, so not only do you have the hodgepodge on the surface, but you have also stratified hodgepodge, I guess I'm liking that word, stratification of all these also. So do you collect just on the surface? Do you collect at what depths do you want it in the water column? So that's where we kind of come in and realize that just not one tool is going to be the best way to collect data. So we want to kind of have it all collected in the same time and space so we can do the best comparative analysis. So you go to the next slide. So we'll have we'll have grab samples. They'll run under the microscope to kind of get an analysis, toxin analysis for that, filter the water out and see if they can get a toxin analysis on it. We also have a wire walker, which is actually Scripps has one. We were just talking about it. They have one on the Sally Ride, which actually uses wave action and it will drive a water quality sonde, such as the XO2 you see here. It'll drive it up and down the water column using the wave power. It actually is a ratcheting system that will ratchet the payload package to the bottom. It'll click a release, and the package comes back to the surface just to repeat it. The crazy thing is this wire walker was really developed for ocean use, but I was talking to the team earlier and I kind of laughed at Dave. I've known Dave a long time, so we can kind of laugh. I didn't think this would work in the lake, but this lake does have enough afternoon wind generation that the waves actually produce enough force to actually ratchet this thing down the water column. And they got amazing results from it. And finally, what we're going to really focus on is an autonomous vehicle, how it can actually get a HAB survey at at all in one time and space. Next slide, please. So the autonomous vehicle used is called the i3XO, or we'll call it an EcoMapper. The i3XO is just the newest iteration of our submersible autonomous vehicle. So we just kind of use that the single encompassing word of EcoMapper. This is a multi-sensor autonomous vehicle. The best thing about it is it actually has the ability to get multiple sets of data and tie it all into one time set. So you're not worried about having to do it manually. It can be deployed by 1 or 2 people. Really, it's not too heavy. It's more bulky than heavy. So one person can easily deploy it. Its mission life can be 6 to 10 hours, up to, 1 to 4 knots, depending on the actual conditions and payload package. And the sensors we used for this project were total algae, pH, DO, and connectivity and temperature, which we like to call the photosynthesis package. But besides water quality, we also have multi-beam side scan sonar, which we didn't think we would need here, but since we had it, we used it. A DVL for bottom tracking, and integrated Wi-Fi so we can easily do data up and downloads. One thing our vehicle has also, next slide, please, is we had on this called an INS, and it stands for Inertial Navigation System. So with a lake like Clear Lake, you have potentially a lot of boat traffic. So, and a lot of fishing, right? And when we were out there, we had water skiers and wakeboarders and inner tubers and stuff like that. So we have an expensive piece of equipment that we don't want to come to the surface very often. So the INS will actually allow this to stay underwater the entire mission. So if you look at the upper arm transect there, that's nearly 12 kilometers. And the inertial, the INS is so accurate that when it did come up, it came up at only 23 meters from its set destination waypoint. So on this one, we set it at 2.5 knots with a depth from bottom of 2 meters from the bottom and 1.5 meters from the surface. So we did this in an undulation pattern, which in the lower left picture you can see. So that way we can actually get not just a line survey, but we can actually get that vertical profile in the water column as we're driving. The fun part about it too, as soon as this thing picks up, as soon as it comes to the surface, it actually will send a satellite signal saying where it is, and easily comes right to my phone, so we can actually get the GPS coordinates too, so we can kind of find it right away. We turned it into a game though, because it was a challenge to see this thing right on the surface, and the only thing that shows up is the little teeny orange antenna that you can see on the top. And once we did this, we have a program in it called vector maps, which we use to plot, but we can actually use vector maps to do a really quick survey of the data to see if there were any interesting points that we may want to survey again, or really just to see if it worked in the first place. Once this thing goes underwater, it's underwater. So I call it like we have the pucker factor, that you have an expensive piece of equipment going under the water and you hope you're going to see it in 2.5 hours. So it's always a sigh of relief when we finally see it. But once you have that data, you can actually import that data to HYPACK, like Tom mentioned, or even MATLAB, which is what Dave's lab used. Next slide, please. Now, besides the undulation pattern that you saw, and very similar to what Tom talked about with the rQPOD, is we can do a lawnmower pattern. And we did this in Konocti Bay, which was very fun because there was a lot of boats, a lot of mooring lines here too. So it was a challenge to set this up. But we set this at 1.5 meters underwater, basically just to avoid boat traffic. You can always set it up to undulate through this pattern, but we just wanted a simple bathymetry report of this area. And as we were saying earlier, when you're doing samples, you know, and you can't see that stratification, if you see in the upper right picture there, you can do a grab sample, but it's still just a couple meters underneath. It'd be nice to see how accurate those grab samples are. In this picture, you really can't see it from the drone picture, but you were seeing lines like wind lines of aggregations of the surface algae. But we'll talk about in a little bit. You kind of didn't see too much of it when, or you saw a different kind of aggregation when you were just 1.5 meters underneath the water. Next slide, please. And this is just showing our deployment. We have Dave perching over the back of a small rented ski boat. It can be 1 person or 2 person deployed. We also have, as you can see, we were in our COVID response outfits last August, which was interesting to say the least. But you do have the ability, Sean is on the middle and the right picture, of launching this with just 1 person. We can launch this off a boat, but it's not limited to just that. That's one of the benefits of having an autonomous vehicle is you don't need a boat. You can launch this off docks. You can launch it from the shoreline. We've actually launched it not too far from where Scripps is, down in Imperial Beach. We launched it in the surf zone to actually do bathymetry surveys right there of some pilings that they had dumped. I'm trying to remember what year it was. But anyway, it can go in and out of the surf zones. Next. Oh, that's one thing. The biggest thing is when we did these missions, we could have all squeezed all 3 of those missions plus Konocti Bay into 1 day, but we had extra time. So we kind of wanted to really kind of stretch it out and kind of weed stuff out and like kind of really see what we can do with this and not be rushed at the same time. So it was kind of a learning process for Dave's team, for me, myself, because I don't get to play with this as much. So it did take, most of them were 2-day trips. Some of it, like I said, was to kind of fine tune it for our June of this year's trip was basically, we only wanted to do in the morning because I think we happened to pick the hottest week of the year and the temperatures were predicted to be up in the 110 plus range. So we wanted to get on the water and off the water as quickly as we can. So anytime we do any kind of service, we always build in a weather day or worst case scenario days, as I like to call them. So it was just kind of a way to, like I said, learn more about the actual system and then kind of take our time. So next slide, please. So there it is. Andrew just put up a link to our white paper that has just been released with, I think Stephanie said today. So we have this as a download that you can see the project we did up there. So we're kind of seeing what's going on. With that, I'm going to pass it back to Stephanie so she can actually talk about the actual results.
Okay, thanks very much, Adam. And as Adam mentioned, we just released this white paper, which has a lot of data in it, but I'm just going to hit some of the high notes here so that you can get a taste for, what can be done. Of course, a survey like this can generate, honestly, more data than you might know what to do with sometimes. But what we're showing here is a nice integrated data set that Dr. Kieran's team generated using MATLAB. We have data from the upper arm, which, as you can see, is the shallowest arm of the lake, the Oaks arm, and the lower arm. And notice that these depths are the same across all of these graphs. We are looking at temperature, dissolved oxygen, and chlorophyll. Obviously, we also have the other parameters, but these were the ones that we were most interested in for this study, it being a harmful algal bloom study. As you might expect, of course, temperatures were always higher at the surface, but definitely you can see that the upper arm generally had warmer waters, whereas the lower arm, particularly deeper areas, had cooler waters. Now, this scale is not a huge difference. It's about 3 degrees Celsius. With dissolved oxygen, we see some very, very interesting patterns. You see sort of vertical stratification of dissolved oxygen in the upper arm. And that's one of the interesting things that you can see by doing this type of a study. You wouldn't see this if you had a static monitoring station necessarily, but this gives you an idea of the type of heterogeneity there can be both vertically and horizontally. I think it's pretty interesting that you see this column of slightly more oxygenated water. There may be something churning the water there. It may have something to do with wind patterns. It could be a lot of different things. Interestingly enough, you see something quite different in the Oaks arm. You see a much wider range, first of all, of oxygenation. And you see something similar to that in the lower arm, but you do see heavier oxygenation in the Oaks arm. You know, one could speculate this may be due to photosynthetic production. Definitely primary productivity is very high in the Oaks arm, where there was a lot of algal activity. That correlates pretty comfortably with what we see with chlorophyll as well. I can tell you that oftentimes when people use the total algae sensor to look at chlorophyll, they see something a lot like what you see in the upper arm, where you think there's a lot of activity, but when you really interrogate it with a chlorophyll sensor, you don't see much. You only see about, in this case, about 10 parts per billion of chlorophyll. We definitely saw a lot more activity than that in the Oaks arm. And that seems to correspond well with where we also see a lot of oxygen. This is a pattern one might expect from photosynthetic activity. And then we see something quite different than looking in the lower arm. So in the lower arm, where we see a little more dissolved oxygen, we see a little bit more chlorophyll, but definitely not the striking differences that you see here. Now, of course, this is something you would want to tease. I'm speaking in very general terms here. You would want to tease these out with some component analyses to see if those correlations really are what we think they are. But one thing that's very important is it is showing you the structural heterogeneity of an active bloom. And I think that's really important when we start talking about where am I going to take a sample, what kinds of conclusions can I draw about what factors are driving or responding to harmful algal blooms. So as another example, we did have these whole lake transects that Adam showed you. For example, we had that 12-kilometer transect in the upper arm. We had shorter transects in the lower and Oaks arm. An interesting thing we did look at was we did collect grab samples in at least 3 spots, or I'm sorry, at least 2 spots, but typically 3 spots in each of these transects. You can see this better in the white paper than I can show it to you here. But something that's really important is the day that we ran these transects, we also collected grab samples from the same areas that we were running the transects. And we did correlations of those single grab samples to the data that were being generated by the chlorophyll sensor on the i3XO. And this is, by the way, chlorophyll parts per billion that I'm showing you here. These correlated very, very well with what the sensor was delivering. But if they hadn't done this and they had just collected grab samples, I think they did this for 9 different days during the month and just took averages, you get a bit of a different picture on what's really going on with blooms in the lake, or what one might conclude about where the most algal growth is in the lake. This is a really important point when you start talking about kind of whole lake heterogeneity, the dynamics that can occur on a very, very tight timeline. And some of you, I've been standing right next to a lake before, and I've watched that microcystis just sink. And if I had grabbed my sample at 9 o'clock in the morning versus 2 o'clock in the afternoon, I would have gotten a very different outcome. So the point we're trying to make here is that collecting data spatially and temporally is going to educate us more about what is really going on in driving harmful algal bloom dynamics. So it's also really interesting then to look at that higher resolution take that we did for Konocti Bay. So this is where we did that lawnmower pattern that Adam showed you. We're always 1.5 meters under the surface. And what's interesting is blue-green algae are pretty much, you don't get a lot of activity. I mean, these are pretty low numbers when it comes to phycocyanin parts per billion. It's pretty low numbers. In this lake, it looked like oxygen activity correlated more strongly with chlorophyll than it did with phycocyanin. I've seen different things in other lakes, and part of the point is that you really have to interrogate your site to understand which sensor outputs are going to be more meaningful for you. The other thing that's really interesting is we didn't see, if you look at a drone image of Konocti Bay, there were like really clear stripes of algae. But when you're 1.5 meters under the surface, you don't see that same type of pattern. And that's, again, emphasizing the point that the spatial heterogeneity in a harmful algal bloom is really something we should be taking more of a look at when we're trying to understand bloom dynamics. So what we learned was that we did get 2D spatial coverage that enabled us to co-locate water quality parameters with data that were collected using discrete samples. We don't have a lot of that toxin data for you yet, but you can definitely see some more of these data in that white paper. But we also saw that the cyanobacterial biomass didn't appear to exhibit the same degree of spatial heterogeneity often observed at the surface. So that was that last point I made was, we had these stripes of aggregates of algae on the surface, but underneath, we didn't really see that. You see a different type of distribution pattern. We are planning to do more missions. In fact, the team has already been out again this year, and we have another couple before the end of the year. So we're going to continue adding to this repository of data and adding to our understanding of algal bloom dynamics in Clear Lake. So I would love to sell you an i3XO, but actually, as Adam has said before, it's painful to admit it is pretty expensive technology. Just coming clean with you, the instrument that we used in this study is about a $400,000 setup. It has all the bells and whistles. Most EcoMappers that we sell are not that expensive. They're usually about half that. To about 250. That's what most EcoMappers usually run. Definitely that inertial navigation system that Adam talked about is one of the big cost drivers on our system. But you have to think about some other things, and you guys being in oceanography can appreciate this because you use a lot of the big tech, but you have to make sure if you're going to make that investment, you're going to be using it a lot. You know how to take care of it. You're able to deploy it. Really figuring out what features you really need. Do you need all of them? And of course, these days, everybody has to calculate the return on that investment. So we wanted to point that out because the way we did this for Dave was as a service. And instead of $400,000, it would have only cost him about $20,000 for us to operate at that site for 2 days collecting all these data. And actually it could have cost him even less. As Adam mentioned, we probably could have done all of this work in a full day, which would have been even less expensive. So we do provide these services if that's something you would like to learn more about. And we also have kind of this funky little survey that we put online that you can use to evaluate whether one of the many vehicle options we have is a fit for you. It can, help you come to the table to have a conversation with a specialist like Adam to figure out if one of these vehicles is a fit for your project. So here is the contact information for myself and my colleagues. Gwen, we're very, very happy to answer any questions that you or anyone else in the audience may have.
Great. I'd like to thank our speakers and YSI and your colleagues that are also on the line for setting up today's call and preparation towards this meeting. I'll remind people if they have any questions, please feel free to throw them in the chat or the Q&A feature below. We did have a few requests come in the registration before the meeting that I'll call out now. So Stephanie, you were just speaking to the cost of the hardware, but we had a question related to operations. And I'm sure that changes just depending on the use, but if you could comment on that.
Right. That's a really important question. So we can start with that figure that I gave you that, for 2 days of operation for us, it would have cost about $20,000. Now, if you talk about your sustaining operational costs, that really largely comes down to taking care of the sensors on the vehicle. So the exosonde, the sensors you have there are going to need to be calibrated. You have to keep an eye on the battery power. The new platform has a good replaceable battery. But honestly, once you've got the vehicle, the operational costs are not that high. It really doesn't get much beyond what you would normally do to maintain those sensors. Tom, you have a lot of experience with these vehicles. I don't know if there are any other hidden costs in taking care of them that you think we should make people aware of?
No, I mean, you've pretty much covered it, Stephanie. I mean, like you said, you mentioned like storage and transportation. That's one of the big things is getting these vehicles into the field. They are, they can fit in the back of most pickup trucks, SUVs, minivans, but that's just a consideration to have. If you don't have access to one of those, how are you going to transport it back and forth to the field? Things like that. But no, I would say that like you said, the operational cost, once it's the initial purchase of the vehicle, it's a big cost, and then once you have it, it's very minimal. 10% of the initial purchase price over 3 years, probably. That would be a rough estimate.
Yeah.
So.
And I would add to that, I'm glad Tom mentioned shipping because that i3XO, by the way, it breaks down into a couple of Pelican cases, which actually makes it much, much easier to ship and move around. So that's another thing that makes it easier to handle than it might first appear just from the pictures.
Got it. Thanks. Adam, you touched on this, but we had a request to speak about feasibility of these technologies in the surf zone, and we're mentioning a deployment in Imperial Beach. Could you speak to that a little bit more?
Yeah, actually, I added that part because I pre-read your questions, so I was kind of ready for it.
Nice.
We did training there, so it's basically it can handle going through the surf zone itself, but when we were doing the work there, it's not like it's meant to ride parallel to the waves or anything like that. It's meant to cut through the waves, surf back there, but it can go within just several feet of the outside surf line. Depending on the depth of where the water is and the actual wave action, you probably aren't going to get the best resolution for if you're doing bathymetry, but you would get the resolution for water quality. For Imperial Beach, like I said, it was a training exercise. There's a bunch of pilings over there, so we're able to scan those, measure them, and actually individually count how many pilings were on the outside of the jetty there, or the pier there. And then we watched it come right back in. It surfed all the way through, and we basically went up to our waist, grabbed it, and carried it right back out. So it wasn't a bad way to spend a training day. I hope that answers it. Basically, yeah, anything that you're not comfortable walking through, don't launch it into it. But Imperial Beach wasn't too bad.
Got it. Okay, and the last question that we received ahead of time was to comment on high-speed communications and specifically video from the AUV to shore.
So I'll take this question. There are video options for the EcoMapper for photogrammetry. So it has a high-speed camera and high-speed LEDs that it can take images of the bottom. You don't have access to that data in real time, though, due to its size and bandwidth and the vehicle spending most of its time submerged. It can't transmit that data. One of our vehicles we didn't touch on today is called a HiCat, and it's a larger surface vehicle. It does have 4K video, but that is more for the operator for navigational purposes. It's not recording that data, but that doesn't mean it can't be. It's just initially not set up that way to record that data. So, but there is 4K video being transmitted back in real time to the operator at the operator's console. It's a forward-facing camera.
Great, thank you.
Well,
All right, I see one question coming in on the chat here for Dr. Smith. Could do this work, the lake work in a day or two at certain cost. Can this type of work be contracted as a service?
Absolutely, and that's actually something new that we just launched. And so the slide I have on the screen here is a link to the page that talks a little bit about those services. And you can always contact Adam. You know, as you might imagine, there's a conversation that has to happen about what your objectives are and the type of water you want to work in. You know, what's at sea state, what type of vehicle really is a fit. We have 3 different vehicles that are available to be contracted as a service. Before you ask it, it usually happens right after that question, we don't rent these vehicles out. I already told you what the price tag was on one of them. We're not generally inclined to rent that out to someone. So our approach then is, you rent us out, you know, you can hire us to come and operate the vehicle for you. So we are more than happy to do that.
And I'm going to add to that too, Gwen, really quick. Besides just the vehicle and operations, we have a tiered system for data too. So we can give, actually this is to Matthew, we can give you all the raw data you want, or we can actually go through and QA/QC it and that write you up a nice little report. I want to say we have like a 4-tiered approach to the data too.
Well, great. Thank you everyone for your comments and your questions. Dr. Smith, if you could put the contact information up again, if anybody has questions, I'd like to follow up with you. All right. And for the audience here, I would also be happy to be of assistance in connecting you with our speakers too in the event that you can't find their contact information. I'm going to share my screen again. And remind our audience that this presentation, as well as presentations of our past speakers, you can find online at the website for the Scripps Technical Forum, which is stf.ucsd.edu. With any suggestions or feedback for our speaker series, please feel free to reach out to Douglas, Vanessa, or I. We really welcome your feedback in order to make this a worthwhile series. We'll have presentations later this month and in the early fall by Kongsberg, RBR, and Subsea Imaging. So keep an eye out for our emails on that. And with that, we'll close. And again, I'll thank our speakers, Dr. Smith, Adam Willingham, and Tom Goucher. Thank you. Have a good day, everyone.
Thanks very much for having us, Gwen. Thanks everybody for attending.